Hello, I'm back again, and now let us take a look at an organic chemistry question. So this question is about organic acids and organic bases. So the first part of the question is about an organic gas phase dianion, DeB2-, which is the strongest base known. So it said that it's produced from compound A, which is a disubstituted benzene containing two R groups. We don't know what R is yet. So draw all the possible structures of C6H4R2. It's quite easy, the first part, but the question soon gets much more interesting. Okay, so the first part. Would you agree with me that I can draw three different structures? Okay, so we are done with part 1. So let us take a look at the next part. Okay, yes, the molecular formula C12H6O4 and effervesces on addition of sodium hydrogen carbonate. Note that this is a property of only the carboxylic acid group. Okay, so we know that aside from the two R groups, the benzene ring has the formula C6H4 because two hydrogens have been substituted. So we'll take a look. C6H2O4, and this forms two R groups. So each R group is C3H02. So we know that on one end there will be the COOH, and that takes one C, two O's and one H. So we need two more C's. And the only way to connect the C's without needing to add any more hydrogens is through a CC triple bond, which is called an alkyne functional group. Okay, so I'm going to suggest that this is the structure for R. It's an alkyne connected to a carboxylic acid group. Okay, so I will soon know whether I'm correct by looking at the next part. So it talks a bit about this spectroscopic technique called NMR. So we don't really need to understand how NMR works. You just need to understand that NMR is able to differentiate the different what we call chemical environments of carbon atoms. So say I have a structure like this. How many different carbon environments are there? So do you agree with me that this carbon is unique, right? There's no other carbon quite like it in the molecule. Whereas on the other hand, these two carbons, they have the identical environment. These two carbons over here, they have the identical environment. This carbon over here, identical, and so on and so forth. And then two more. So how many carbon environments are there in this molecule? Which is how many signals the NMR will show. It will be 1, 2, 3, 4, 5, 6, 7. 7 signals. So they say that compound A is found to have 6 signals in the NMR spectrum. So we are asked to deduce the structure of compound A. So compound A, the R groups, assuming we got the R group deduced it correctly, it's most likely we deduced it correctly, then it can be situated at different positions, right? So let me replace the R groups with the R group which we found, which will be C triple bond COOH. Hold on, sorry, I made a mistake. C triple bond then COOH, C triple bond C, then a COOH, C triple bond C and a COOH. Yes, I know that the geometry of each of the alkyne carbons is linear, but I really don't have any space here to work with. And last one. how many carbon environments are there for the first one. So we have 1, 2, 3. So the carbons that are labeled the same number have the same carbon environment. 4, 5, and 6. Okay, so this certainly looks like a possible structure, am I right? So let us take a look next at the next structure. So how many carbon environments are there in this structure? 1, 2, 3, 4, 5, 6, and 7. So this structure is out. And let us take a look lastly at this structure. So 1, 2, 3, and 1, 2, 3 is identical. 4, 5, and 6. So we have two possible structures here. So is there any way for us to see which structure is correct? Let me take another look at this. Oh, I made a mistake. Can you spot where's my mistake? 5 and 6 actually have the same chemical environment, right? So there's only 5 different chemical environments in this one. So this is wrong. So there's only one correct structure, which is this. So what is the structure of compound A? We can write it down. Compound A. Okay, we got the structure of compound A. So compound A forms DeB2- via these two intermediates to the removal of positive ions or neutral molecule from the substituent R. So we know that the benzene ring is not changed. So let us take a look at the possible structures of B2- and C2-. So what is the MR of compound A? Let us do a quick calculation. 1,5. Wait, hold on. Sorry, made a mistake. 214. So 214 to B2-, you are minusing 2. So and you are also getting a charge of 2-. So I suggest that 2H+ has been removed, which will be the acidic hydrogens. So B2- could be this. Certainly it's a possibility. Then going from here to here, we are losing how many grams per mole? 44. There's a 4 in the MR, 44. Let me propose to you, could it be that this 44 comes from the loss of a CO2? Right? So this CO2 is lost. So how could this mechanism occur? This could certainly have occurred, right? So a neutral CO2 molecule is released, and this carbon over here gains a negative charge. So we don't really need to draw the mechanism, but understanding a potential mechanism can help us convince ourselves that indeed C2- can have this structure. and the other group will not be changed. Hold on, I'm getting ahead of myself. The only one CO2 group has been removed. Okay, so from C2 minus to DEB2 minus, you realize it's another minus 44, which is another molecule of CO2 being removed. So DEB2 minus, we have gotten its structure fairly easily. Okay, so that wasn't too hard after all, right? So do you know why this is a very strong base? Why? Because carbon has the negative charge here. Now we all know that carbon is not a very electronegative atom. It's a small and fairly electropositive. So it does not hold the negative charge very well. So it will have great energy stabilization if it were to take a proton from another species. So it is a very strong base, but it is still considered fairly stable. The reason behind it being fairly stable is that because this negative charge, right, is held in a sp orbital, right? Am I right? And this sp orbital has fairly high s character, right? 50% s character. So the negative charge is held, the lone pair and the negative charge is held in a orbital with much s character, which is close to the positively charged nucleus, helping to stabilize this carbon ion. So while most carbon ions, they are very reactive intermediates, this one is potentially a stable reagent. So let us now take a look at part C. It is a structural elucidation question. So let us look more into it. An organic acid, C7H10O2. Okay, so we first calculate the degree of unsaturation. So 2 times the number of carbon atoms plus 2 minus the number of hydrogen atoms divided by 2. That will give us 2 times 7, 14, 15, 16, 3 degrees of unsaturation. Am I right? So it's an organic acid and it has 2 oxygens, so suggesting that one of the degree of unsaturation comes from the C-double-bond-O in the COOH group. And we know that compound D decolorized bromine water, so perhaps there's 2 C-double-bond-Cs, 2 alkene functional groups, a possibility. So it is reflux with acidified KMNO4 to produce only one organic compound E. So we have a C-double-bond-C and now there's acidified KMNO4. Certainly we will come to mind what? The oxidative cleavage of the C-double-bond-C would have occurred. And it's the only one organic compound. So it loses 3 carbons, and these carbons, I presume, will be lost in the form of carbon dioxide. So now I'm going to propose a structure. It may not be correct, but I'm just going to try, okay? So C7, so I assume it's linear. I may be wrong, but it's okay. We always should try first. And then at one end is the carboxylic acid, 2, 3, 4. So I would draw it like this. So what is the thought process behind this? Because when oxidative cleavage occurs, right, here and here, so this will become COOH, correct? And then will that be the correct formula? C4H6O4, 1, 2, 3, 4, C4, H1, 2, 3, 4, 5, 6, correct? O4, so that will be correct. And then what will this be? This will form ethane dioic acid, which will be further oxidized to carbon dioxide. And this one, terminal carbon, will just be carbon dioxide, right? So certainly a possibility. So let us keep that in mind first. Keep this structure in mind. it could end up being the right answer after all. Right, so let us erase this first. Erase this brown annotations. Okay, so let us see what else the question says. Okay, so gentle heating of the anhydrous crystals of compound E. So if the structure of D is correct, then consequently the structures of E, the only organic product would be do you agree? And we see that gentle heating of the anhydrous crystals of compound E produces a neutral compound F. So from E to F, there's a loss of a molecule of H2O, right? Minus H2O, 2H and 1O. Most of the time, it will be lost as water, since water is a fairly stable molecule, and this is called a condensation reaction. So you just gentle heating without any reagents. So this is interesting. It's most likely a reaction not in the H2 syllabus. In fact, I do know what the reaction is, but I assume that most H2 students will not know, so I'll pretend as if I don't know. And it does not react with sodium metal, so it is no longer acidic hydrogens, and does not give a precipitate with 2,4-DNPH, means it's no carbonyl, that means no ketones or aldehydes, so no carbonyl groups. So it lost a molecule of water. So we know that we know some other reactions where a molecule of water is lost. For example, and over here we suggest that it's an intramolecular reaction. So we know other cases where water molecules are being lost. So for example, there can be a esterification, intramolecular esterification. You certainly have heard of this before. Okay, maybe I add a few more carbons. Okay. To form this, right? And then minus H2O. So can something similar occur here? Right, I remove a OH here and a H here. And then what would I get? I'll get something like this, right? And really fulfill the properties. It does not have any carbonyl groups, no, because this is like something like these two C double bond O's, they are not carbonyl groups. Right, because they are bonded to oxygen. In fact, this is called an acid anhydride. For those who know, it's considered a carboxylic acid derivative, and it behaves very similar to an acid chloride, as you will see later. But okay, so this could be compound F, highly likely. It could be compound F, no acidic hydrogens and no carbonyl groups. Compound F reacts with ethanol to form G. So what is formula of F is C4H4O3. To this, what do you get? You get plus C2H6O. What is the formula of ethanol? C2H5OH, which is C2H6O. Right? So basically, one molecule of ethanol just adds to it, right? So we have to think about how this will occur. So most likely, am I right, that this is going to react in a similar way to acid derivative, right? So I propose now that this is a nucleophile, and it attacks this electron deficient site over here, and this goes, and then we get and you get something like this. Okay, I know that the actual procedure is that the double bond will break and then reform, then this will go out. Yes, I know the mechanism of nucleophilic addition. But for simplicity, we'll just keep it as such. and then there's a OH here, a plus, then very simply the H will get just transferred over here, and then you'll get this. So okay, this is a possible answer for structure, what is it, G. Okay, and then we are then told that compound F is methyl amine to give a compound H. So from compound F to methyl amine over here, what am I adding? I'm adding CH5N. And what is the formula of methyl amine? CH5N. So also adding everything in. So let me propose to you something similar. So instead, the nucleophile will be CH3NH2, and then what will you get? This is it H? Is the name H? Yes, the name is H, and then we will get something like this. Okay, is that the right formula? H9NO3, C5, H, 1, 2, 3, 4, 5, 6, 7, 8, 9, one more here, and NO3, correct. So it gives a salt reaction in NaOH. Yes, it does, right? Because this acidic group can react with NaOH to give a carboxylate salt. Does not react with HCl, yes, because the amide group, as you have learned, is neutral, it's not basic, right? Because of the resonance, the lone pair on N can delocalize into a C double bond O, making it not available for donation. Compound H does not display enantiomerism. So now let's take a look. H, is there any chiral centers in our structure? No. So perfect. Both compounds G and H produce E on heating with dilute sulfuric acid. So G, when what happens when heat with dilute sulfuric acid, right? Basically there'll be a hydrolysis of this ester. Okay, I erased too much. Hydrolysis of this ester, right? Hydrolysis of this ester to produce back E. Will I produce back E? Right, well, what happens when I hydrolyze this ester? I will get sulfuric acid, right? So it is acid hydrolysis. Yes, indeed, I get back E. And what if I do an acid hydrolysis of this? I get correct and correct. So I get back E again. So okay, this is my final answer. Let you guys take a look, convince yourself that it fulfills all the requirements, right? Okay, so D organic acid is this. It reacts to form it reacts with KMNO4 to form E. Yes, and heating E gives F, this acid anhydride over here. Reacting it with ethanol gives G, and reacting it with methylamine gives H. So that will be my answer, and that's the end of this question. Thank you so much.